When we're adding a web interface to our Micropython projects, we have to make sure that our code doesn't get stuck waiting for our HTTP requests. So in this tutorial, I'm going to show you how to use both asynchronous coding and multi-core programming to get around this blocking problem. Hi and welcome to BytesNBits. If you've been following through in this series, we'll have had a look in the previous two tutorials, firstly at how to get a Wi-Fi connection up and running, and then in the last tutorial, how to build our own web server that can handle file requests and REST API requests. Now, if you haven't seen those videos, then do please have a look through. I'll put links to those in the description down below. But at the end of that previous tutorial, we did come across the idea that our standard code does have a major problem. The standard way in which we receive an HTTP request over our Wi-Fi connection uses what's known as a blocking function. And that really means that our code will sit on that line in our program waiting for the HTTP request. And our processor's then not able to go off and do anything else in the meantime. So in this tutorial, we're going to look at how we can get around that in two different ways. The first will be using what's known as asynchronous programming, and that will work for any Micropython enabled processing system. And the second then will use dual cores. So I'm using a Raspberry Pi Pico for this tutorial series, but if you have something like that or a ESP32, some of the variants on that, they do actually have two cores in the microcontroller. So we can simply offload some of our programming onto that second core, which then lets our first core just run in sort of normal mode. So let's have a look at how we can get around this blocking function and get onto our Raspberry Pi Pico. So let's start by just examining what's going wrong in our main blocking code. So at the moment, our code lets us open up a socket, and we then bind to that to get our HTTP connection. And after that, we then start our main program loop, and we then try and accept a connection through this HTTP channel. And this is really where we have our blocking function. This accept method on our socket, it really just sits there and it will halt our processor waiting for this HTTP request to come into. And really what that means is that the next lines of our code don't actually run until we receive that connection. So in some instances, this is absolutely fine. So say we had perhaps something like a weather station and we wanted to produce a web interface for that, where we're just simply going to use that to have a look at what the current situation is. Then if certain things are happening while we're not looking at it, then that does not really make a difference. But if we were perhaps running a robot, then obviously we would want our microcontroller to be able to run the control software without it being blocked, and have our web server then running in the background. And that's where we're going to start looking at something called asynchronous programming. And of course, another route round that with something like a Raspberry Pi Pico is of course to have our control and web server running on different cores. So that's where we're going to have a look at our multi-core processing. So we're going to start with the asynchronous solution. And for this, we're going to be using one of the Micropython packages called uasyncio, which is the Micropython version of the asyncio main Python package. And really what this lets us do is to divide our code up into a number of tasks or coroutines. And then the asyncio puts a scheduler on top of this, which then uses the single core to time slice each of our tasks. So in other words, we have one task perhaps doing our control software, one task handling our web server, and our scheduler then will slice up the time of our processor and assign time blocks then to each of our tasks. So we get this idea of our tasks running in parallel, or this idea of multitasking. So before we go into the actual code, let's have a look at a test circuit that I put together just to show that everything is working. So we've got our Raspberry Pi Pico, And then I've got it connected to a number of inputs and outputs. So we're using a potentiometer here to just give us a little bit of input. We've got some LEDs here which we're going to be controlling from our web panel. And we then have another LED here which we're going to be controlling from within our control software running on the Pi Pico. Some neopixels down here which are cycling through colors, and again we're going to be running those from the control software inside our Pi Pico, and then 4 other LEDs over here which are going to be again controllable through our web panel. So you can see on the screen as well I've got the actual final web panel, and I'll be covering the HTML and JavaScript coding for that in the final tutorial. But for now you can see here the potentiometer reading. If I adjust the potentiometer here, you can see that we do get our needle changing on our dial. I can then, of course, in these coloured LEDs up here, if I click on the blue one, you should see the blue LED coming on, yellow, green and off. I can then, of course, on the 4 neopixels which are off at the moment, I can of course then increase the red value on there. I can bring in some green and I can bring in some blue, and we can start to play around with the colours on those things. And you'll see as well then we're also reading the inbuilt temperature sensor on the Pi Pico, and then these 4 colour blocks down here, these should relate then to the 4 neopixels which are being driven here, and we should see that the colours are matching up as they cycle through. So really what's happening then, again, our web control panel then is sending signals to our Raspberry Pi Pico as we click things up here. It is receiving back information when we adjust things like our dial and so on. And then it is running in its own control loop. So again, these are making sure then that we're not having any of this blocking code whenever we try and handle our HTTP requests. So our web server, our asynchronous web server then of course is being able to run these loops while we are doing everything else. Now the full circuit for this I will put into, there'll be a link to that in the description. So every project tutorial that I do, there is a full web page that I create on my bytesnbits.co.uk website. So if you head along to there, you'll get the circuit diagram for this. But again, I'm going to go through the code mainly in terms of how the async software and eventually then the dual core software works, rather than focusing on how I'm driving these outputs. But if you do want to mimic this and use my software, then obviously you can go there and get the actual code and circuit diagrams. But now that we understand we have a test circuit that we can use just to see that everything is actually working, let's jump into the Pi Pico code and see how we actually implement this asynchronous web server. So the code file I'm looking at here is this API_async. And again, all of this code will be available as a GitHub repository. And again, you'll get links to that in the description, and also if you go out to the main tutorial page on my bytesnbits.co.uk website. But if we have a look through here, I've done a bit of refactoring since the previous tutorial just to make things a bit clearer in the code that we're going to be looking at now. So I have extracted the Wi-Fi connection software all out to its own object. So really this call here is going to set up the Wi-Fi connection and give us something to bind to in our sockets and so on. I'm also then on the I/O side of things, so the control of the LEDs, neopixels and so on. Again, I've extracted all of that out into its own class here. So you'll see in my code here we'll be making various calls to this I/O handler, and that will just simply be then making sure that the inputs and outputs that I want to read and control are all handled correctly. But again, I don't have to have all the software then, all the code lines actually in this demo code here. So that's just making things a bit easier as we go through the code. Now, to get the asynchronous web server up and running, we do need to import this async IO library. And again, the U there, the uasyncio, is the Micropython version of it. So we import that at the top of our code. And then we just simply need to slightly reorganize the way in which we handle our functions to make them make use of the asynchronous scheduler to allow multitasking within our Raspberry Pi Pico. So if we come down through our code then, so we're getting a Wi-Fi connection up and running, and we then have a number of these functions, but they're defined in a slightly different way. So you can see here that we're using this async keyword, and that is going to make sure that this function that we are defining then is structured correctly to be handled by our asyncio scheduler. And you can see here I've got a number of functions defined as these coroutines in effect. So again, coroutine is just simply a term that the asyncio is using for a routine that can run in parallel. And we'll see in a second there are certain features that it has to have to meet that definition. So I'm defining a couple of handler routines. We're defining a main routine here, which we're going to see in a second actually kicks everything off and gets everything running. And then down the bottom we have the asyncio setup, and this is what actually starts the scheduler and links in the various tasks that we want to run. So you can see here that we're putting it inside a try catch and finally a structure. So we are trying to run the main coroutine. So you can see here that is actually a reference to this function up here. So we're saying to our asyncio runtime, we're saying I want you to run this function. We're going to run it as a task. And then once we've set that up, we're then going to run this bit here. I'm not going to get into details of how the asyncio actually works, but what we need to do is we need to create an event loop which will actually manage our set of parallel tasks. So down here, all we're doing is we're saying we're going to reset and create a new event loop that's going to handle the current running set of parallel tasks, which of course are going to be set up using this function here. So in essence, whenever we want to create an asynchronous system, we're going to define a number of routines that are going to handle things for us. We're going to define one main routine which is going to kick everything off for us, and we're then just simply going to link that main routine into the main asyncio scheduler using these lines of code here. Okay, so let's delve into first of all our async main code. So again, as I said, putting in the async in the front of it turns it into this idea of a coroutine which allows it to run as a task in asyncio. So let's just expand that out a bit here. And what our main code then is doing is going to make use of these two further handlers up here. So we have our two further coroutines which are going to do some of the lower level tasks, but our main routine is going to create those as these ideas of tasks in our multitasking system. So we're using this idea of the asyncio object, we're using its create task method, and we're then passing it some sort of information, and it's going to wrap whatever we pass in here up as one of these task objects, and that will then allow it to run in parallel with other task objects. So you can see we're doing two here. So we're creating in this area here, we're creating a web server, and that will run as one task. We're creating here a little NeoPixel handler. Remember I said on our demo circuit we had 4 NeoPixels that were being run within a control loop. So that's going to handle the control loop for those 4 NeoPixels, and that will be handled as a separate task. Our main routine itself is a task, so we can inside that then run a control loop, and this one here is just simply going to toggle that single red LED on and off. So in fact we're going to end up with 3 tasks in our system. One's going to handle our web server, One's going to handle our neopixels, and one's just going to turn on and off that red LED. But again, that should then show us that everything is running in parallel. So the easiest task that we're looking at then, I'm going to just bypass this one here for a second, is this neopixel handler. So let's have a look at how that actually runs. So if I expand that one out here. So again, you can see it's pretty much just a normal loop, a normal control loop. So we have our while true loop here, and inside that while loop we are doing a number of things. So we're really just creating a bit of a delay. So I'm just simply getting this loop to count how many times it has run, and then every 1000th run it's then going to adjust our neopixel colors. I'm doing this as this sort of counter so we can get an idea of how fast our system is running rather than just making it go to sleep. You will see a sleep option down here, but we're going to come to that in a second. That's a special sleep operation. So every 1000th run through this bit of code, it goes off and then in effect just cycles our neopixels and of course then increments our count. And inside this bit, this is where you would do all of your own I/O handling. So whether that handles various motors, reading sensors, and so on. But we have a control loop here which will run in parallel with our web server. So we've got around that blocking thing. Now I said that these functions are called coroutines, and they have to have a special format to allow them to run within our multitasking system, and that's where this final line comes in here. So our async I/O is actually a rather simple version of a scheduler. So if you think about something like Windows and so on, those are all big multitasking systems, and there are hundreds of different tasks running, and the scheduler has to prioritize certain tasks and divide up the processor time and so on in quite a complex way. And we're not actually doing that then on our Raspberry Pi Pico, because of course it's a much smaller system. So our task scheduler basically has a list of the tasks which need to run. And again, that's where we, down here in our main, so when we kicked off our main task, it then created a number of subtasks which are going to be then put into this thing called our event loop, which we saw being kicked off down here. And on our async I/O will basically start to work through that event loop, running each task in turn. But it doesn't really switch tasks automatically. We have sort of like a semi-automatic system here. So when our neopixel task gets into gets its runtime, it will start to run. And it will keep on running until it lets another task have a chance to take over. And that's where we have these await instructions. So what's happening here is we need to create what's known as an awaitable function. So this here is an awaitable function. And what that means is it's a function that we can execute, but it is structured in a way that allows the event or our task scheduler to allow other tasks to get priority. So what we're saying here is we want to await this function. So this function is going to go off and come back to us at some later time. So we have to wait for it to complete. But while we're waiting for it to complete, that lets other tasks in to run. And that is the whole idea of how the scheduler here works in this async I/O system. So what we're doing here is we are running the sleep task, but we're going to sleep for 0 seconds. So in effect, we're not actually going to sleep. All we're going to do is say, allow some other tasks which might be waiting to execute to get some execution time here, and then come back to me once it's my turn to run again. So our neopixel function goes off, it runs through its loop once, it then says, okay, let somebody else have a go, and put me back on the queue. And then eventually it'll be our turn on the queue again, and we'll get the second loop in our function. And that's really all you have to do to make sure that your function runs as a proper coroutine and lets other tasks in. If we didn't have one of our waitable functions being run in here, then once this NeoPixel task got focus and got some runtime, it would really just hog that and lock out the other functions. So say this little line here where we sleep for 0 seconds in effect just says let everybody else in and then come back to me as soon as you can. So this then will run our NeoPixels then in the background. So that is a simple one, and we could, if we wanted to then, we don't have to do it all in one task. We could have perhaps one task running to monitor our inputs, and that would build up an input table. We might set off a second task which maybe would handle motors and various heating elements depending on what we're doing and so on. And we can really just have them all in their own little separate control loops, and each of them then running in parallel. But the second one that we want to then have a look at then is our web server. So again, as I said, we're going to run that as a separate task, and that will run in parallel then with everything else we're doing. Now the asyncio is actually one of the functions that it's designed to do is to handle things like HTTP requests, and there is actually a web server built into that, and that's what we're using here. So we're creating an asyncio server by calling the asyncio object. It has a start server method. And what we do there is we have to give it a function that's able to handle our HTTP request, and we then bind it to a port that we have already opened. So remember, up at the top here, I am opening up a Wi-Fi connection, and that will create a port for me to bind to. And then we're binding to it in pretty much exactly the same way that we did in our previous examples where we were using a socket to bind to it. So we're binding then just to the in effect whatever socket is available. We're going to then bind to port 80 on that, which is the HTTP port. And any time that we get a request coming in, that will then be passed across to this handle request function, and that will then do the actual handling of it. So let's have a look at that piece of code next. So looking at this code then, we can see that the function definition then is going to accept a reader object and a writer object. So those will be coming across from our asyncio web server. And we just simply need to have this particular structure for our handler. And we're then going to use these, as you can probably work out. Our reader is going to allow us to read the information coming in from our client, so to being able to read our HTTP request, and we're then going to use a writer to send back our HTTP response. Now inside the actual function itself, it's going to look very, very similar to our code from before. So we are going to read in the raw request data, and again we're using one of these waitable functions. So the reader.read method will simply go off and wait until it receives an HTTP request, and it will then read in the information from that request. Because we're using it as an awaitable, while it's waiting to receive its information, it will allow other tasks to run. So in effect, when we execute this line, this particular task will pause waiting for an HTTP request, allowing other tasks to run in the background. And as soon as an HTTP request is received, this function then will return back, and the next time that this task gets a run slot in the processor scheduling, then we will come back in here and we will be able to execute the rest of this code. So again, that's how we're getting our asynchronous web server running. So we wait for our request coming in, and then as you've seen if you've looked through the previous tutorial, and if you haven't, please do, because again that will help make sense of what all of these function calls are. But we created a an object which will receive our raw HTTP request and then decode that so that we can very easily work out what the client is asking us to do. The rest of the NSA is pretty much exactly the same as it was in the previous example. So we're going to create an object which is going to handle our response back to the client. We're then trying to work out what the client asked us to do. So we have an API endpoint here, which allows us to read the data from our potentiometer and our temperature sensors, and also then send back the states of our LEDs and so on. And that's going to return that back, as we can see here, as a JavaScript, a JSON return value. There's other then API actions to set the color of the LED. So again, we're going to be receiving in button presses for the red, green and yellow LEDs, and that will then turn those on and off. And then we have another API function here, which is going to receive in some RGB color values from our web client. And that will then set those 4 other neopixels that we saw working. So that's just handling the request then. If it's not an API call, we're just going to assume then that it's going to be a static file that is being requested, and we're just simply going to see if we can find that and send it back. But in essence then, as I say, that is exactly the same as it was in our previous blocking code from the previous tutorial. So we're going to build up our response. The only difference then is how we get our response back to the client. So again, we saw in the method definition here that we have a writer object being supplied to us by our async.io web server, and we're going to use the write method on that to send back the raw response data. So again, my response builder object has got a build response method, so that once we've set it all up, that will then generate the actual byte string that needs to be sent back to the client, and that's where we then send that back to the client. What we will then do is we will again use these awaitable functions. So once we've kicked off our write, we have a method here that, and this method drain, that will then send it back out to our client. So the browser which we're using to access our Raspberry Pi interface. This function here will then make sure that HTTP response gets sent back out. And again, you can see here, it's going to take an amount of time for that data to be sent out through our Wi-Fi channel. So while that's going out, we're going to wrap it up in one of these awaitable objects, so that we can let other tasks run while that data is being sent out. Once that data has been sent out, this method then will return, and the next time that we get some runtime, we'll be able to carry on. So the next line on this then is we are just going to close down our connection so that we're then ready for our next HTTP request. And again, we're using another awaitable object here, so while that closing down code is running, we don't block our processor. So that's really how our web server is going to run. So you can see, the actual handling of the request and generating of the response is identical to our previous system, but here we are able to use awaitables to so that while we are waiting for data to be coming in and for data to go out, we're not blocking our processor. We are allowing that to run in the background and then coming back once we get some more runtime. So that's our 2 main tasks running. As I said, our main task itself is actually a task, so we can embed in that some other control code here. And again, you can see all we're doing is we are toggling our red LED on and off inside an infinite control loop. And again, we're using this awaitable with the sleep function and sleeping for 0 seconds. So again, once we run through the loop, we're basically going to say, let other tasks have a go and then come back to us as soon as you can. And that really is all there is to our asynchronous system. So again, you can see here that we have our web server is a little bit special, but a lot of that is then it just works, and we just simply have to make sure that we have a handle request method which matches in with its signature, and again with that reader and writer object, and then just simply kicking off our tasks in our multitasking system. So that is our asyncio, and again the running of that, I'm not going to go back to the test circuit each time, because it's going to be identical every single time. Each of these examples is going to run exactly the same control code, but you've already seen there that it does run, and the frequency we're getting here is, so if this is running 1000 loops per flash, we're getting about 2000 loops per second on this particular control loop here. Again, just have a look back at the LED flashing. So that is our asynchronous server. Again, all of this code is in the GitHub repository. So that's our first method of creating a non-blocking web server. And again, this is part of our standard Micropython code, and it only requires one processor core to run this multitasking system. So if your microcontroller board does support Micropython, you can run the Asyncio system on it. Now, the Raspberry Pi Pico and some of the ESP32 boards do have 2 cores in them, and that opens up another possibility in how to get around this blocking web server. We can of course then take our 2 cores and then split our code up into the control system and our web server, and then run them on separate cores. So even if the web server is a blocking piece of code, then it doesn't matter, because our control software is running on its own core, and that won't have any issues. So let's have a look at how we can then run in multi-core mode. So for this example, we're looking at the API_threaded.py file, again, that you'll find in the GitHub repository. The code for this then is going to be very similar, of course, to our normal blocking web server, because we're going to be using all of the same code. It's just simply we're going to be dividing it up into 2 cores. So the ability to use 2 cores comes from the thread package, which we will need to import then at the top of our Python file. Now, this thread package is, if you look at the documentation on the Micropython website, you'll find that it is actually still in development mode, but it does work and is fairly reliable. But let's have a look at how we can then actually use that. So again, I'm coming in and we're doing our usual system where we need to first of all set up a Wi-Fi connection, and that's all that block of code is doing there. And then we need to have each of our functions, or our control and our web server, we need to split them out into 2 separate functions. So here I've got one function which is going to handle the web server, and that's pretty much exactly the same as the web server from our previous examples. And I'm then going to split out a second function, which is our main loop, and that would be perhaps our control functions, which are going to monitor our motors and so on. I'll have a look at the actual details of those in a second, but let's see how we can actually then get it to run as 2 separate cores. So we need to have, as I said, each of our threads as separate functions that will run completely separately. We can then start them on different cores by using the thread package's start new thread method. And really what we're doing here is we're saying we're going to create a second thread, and that will of course put it onto the second core. We're then going to tell it to create a thread, but using our main loop function as the code that's going to run on that second core. And that's going to go and run our main loop. So at this point, we now have the code inside our main loop running on core number 1. Remember, they're numbered 0 and 1. Which means that at this point here, we're still running then on core number 0, and that's where we can start our web server code. Now, I did do some testing on this, and I'd found that the web server software will only run on core 0. If you try and start the web server on the second core, then it runs for a short time and then seems to fail for some reason. So I'm not entirely sure why that is. And again, it might be due to the fact that the thread package isn't completely finalized yet. But whatever way around, if you make sure then that you run your web server on core 0 and then start any of your other code, any of your control software then on the second core and let it run there. So that's in essence, that bit of code there is how we get the two functions running on separate cores. It is that easy. So if we have a look at the actual code itself, so if we look inside our main function then, you can see that again, all we're doing here is we are running a control loop. So we have our forever loop here, and we're simply then inside that doing the various things that we need to do. So again, this is the control function, and in the demo circuit, we were toggling our red LED on and off, and we were also then cycling through colors on our neopixels. Again, I'm putting it in this counter loop so we can see how fast that is running through. And here, we're getting 70,000 loops of simply counting in between each of our updates. So we can see that we're actually running at full speed on this core. So if we then come up to our web server, again, as I said, this is pretty much identical to our previous blocking web server, and in fact it is exactly the same code. So again, our Wi-Fi connection has been established at this point up here. We're then opening up a socket and binding to it at this point here, and then we go into our web server loop where we're just doing a forever loop where we're going to wait for an HTTP connection, and again we're using that blocking method here. So our code and this particular core will halt at this point waiting for our HTTP connection. But of course that doesn't matter because our control code is running at full speed on the other core. And then we go through and we handle that request and cover our API and file serving and so on. So again, very similar to the previous examples. And again, we're using the standard web server code, so we're back to using our sockets and so on. So that really then gets it up running as a two-core or a multi-threaded system. And you can see then that we will be able to run both our web server and our control on our one Raspberry Pi Pico without either interfering with each other. So with this multi-threaded example then, we do still have a slight bit of inefficiency. So our main control system is running and using the full potential of that core. But if we think about our web server then, we're back to that idea of the blocking code. So our core is really going to be sitting doing nothing at this line of code here, where it is in effect halted until we get the next HTTP request coming through. And again, the time it takes to handle the HTTP request and the time in between HTTP requests means that most of the time we're going to be sitting here doing absolutely nothing, and that of course is wasting some processing power. And on these little microcontroller boards, we really do want to make the most of the power that we have. So we know that if we have a single core, we can still utilize that fully by using asynchronous programming. So I guess the ultimate then for our Raspberry Pi Pico is to combine both our multi-threaded coding, so that we then use two cores, with our asynchronous coding, so that the core that is handling our web server can actually get on with other tasks while it's waiting for the next HTTP request. So let's have a look at how we can combine both of these techniques to make full use then of our two cores in our Raspberry Pi Pico. And of course this will be identical then to running it on something like the ESP32 with the two cores. So the file API full demo, this contains both our multi-core and our asynchronous multitasking systems all combined into one file. And if we look through that code, you'll see it very much is just an amalgamation of the two blocks of code that we have been playing with in this tutorial. So we can see we have our asynchronous HTTP request handler here, and that is exactly the same code as in that part of the tutorial. We've then got our coroutine, which is going to be our main function, and that's the one that actually kicks off the tasks. And if we have a look inside that, you'll see that we are kicking off our web server. I have extracted the NeoPixel handler out of here. Remember, in the previous example, we had a second task running for our NeoPixels. And then just leaving the task inside this main loop to toggle our LED. So in our asynchronous server or asynchronous core, we're going to be running a web server and then just a simple toggling the red LED. The NeoPixel handling then, I have extracted that out to its own separate function here, and that's what we're going to run on the second core. So at the very bottom here, again, we're just amalgamating the two parts of our setup. So we are setting up a second thread, so that will run on core number 1, our second core, and that will use the NeoPixels function then to run the code there, and we're just simply starting that then as a new thread. So that will give us our multi-core processing. And then on our core 0, and again we do need to keep our web server on core 0 even in asynchronous mode, we then are running that up, and again you can see we're just simply doing exactly as we were before. We're setting up our main function pardon me, as our main task, which kicks off the other web server task, and then generating our new event loop. So very much this is just simply putting together those two pieces of code to give us both the asynchronous system running on core number 0, and that will handle our web server and give us a little control loop, and then using our second core with a second thread to handle a second control loop, which in this instance is just going to color cycle our NeoPixels. So that really is everything set up for that, and that really is as far as I'm going to take our Micropython web server software in this set of tutorials. One note on how you split things up. So again, we now have the options of putting things on separate cores. We have the options of putting things in one core but in multitasking mode. Obviously running something in a second core. So here we're using our NeoPixel handler to run as a separate core. That core will of course be running at full speed. So whatever software you run on there will not get interrupted by anything else. So if you're doing some timing critical stuff in there, I would suggest that you run your timing critical stuff as a thread on its own core. That then leaves our asynchronous core, which is handling the web server, and you can see here that I've left in that little bit of control code there, which is toggling an LED. Even though we are multitasking that core, there will be times, of course, when our control code here does not have focus and our web server is doing things. Now, the way we've structured that web server, mostly it is using awaitables when it's handling data transfer. So the data transfer, which tends to be the slow things in our microcontroller circuits, that is not going to block our main control loop. But of course, once we receive a request and we have to handle it, there may be some extra processing goes on at that point. And of course, that will create a delay where our web server task has got focus and is processing that data, and during that time, of course, our control loop here will not have any processing time. So if it is doing some very time critical stuff, then depending on what speed you're decoding and handling HTTP requests, you might have little dead blocks inside your control. And of course, if you are handling motor control and things like that, then that can cause an issue. So in breaking up your code, do have a think about whether it needs very fine timing when it would handle best on its own core, or whether it can be a little bit flexible in its timing when you can then use that extra time on our asynchronous side of things to just do a little bit of sort of housekeeping and general control, which isn't as time critical, as I said. So that covers all of the code I want to do on the Raspberry Pi Pico or ESP32 side of things, on the Micropython side of things. All that's left now is to have a look at the actual web interface, and really that is not so much Micropython code. We're now looking at our web code, which is going to be a mixture of our HTML, CSS and JavaScript. And I will be covering then that in the next tutorial. So if you are following through on this, do make sure you subscribe to the channel and click that notification button to make sure that you get a note as to when that next tutorial is live on YouTube. I hope you're enjoying this. I hope you're finding it useful. A lot of these techniques, although we're using it here for our web server side of things, the asynchronous coding and the dual core processing, of course you can apply that to whatever you want to do. It doesn't have to be for handling HTTP requests. So do make sure that you put that into your programming toolbox and use that. So hope you enjoyed that. I look forward to seeing you in the next tutorial, and bye for now. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.